Good morning. I'm going to try doing this Chapter 1 lecture again, see if we can get it uploaded. You'll see these slides at the beginning here giving some worked examples. These would actually be from your Chapter 0 in the second edition. We discussed these in the class discussion. I'm also not going to spend too much time on those slides that we did cover quite a bit in the class discussion. I'll just give a brief overview. So one of the things, obviously, is to be able to convert units, and we've talked a bit about that already. This worked example shows you how you can convert Fahrenheit to Celsius. You should be able to do this from Fahrenheit to Celsius and in the reverse. You should also be able to convert to the Kelvin scale as well. So there are formulas in your text for each of those conversions. I would suggest that you have those on your exam sheet when you come in for the midterm and then the final exam. Another thing just to note here, they're showing you two different approaches, the thinking approach and the formula approach. As we get more involved in different types of problems, the thinking approach will help you in terms of figuring out if you're applying the correct formula and setting up the problem in the correct number of steps. Most of the time the problems that they'll work in, I'd say probably from Chapter 3 on, may have multiple steps to them. So a good way to start doing those is to think about the different steps you're going to do first and then run through and do those. And always make sure that you're writing down what you're doing so you can always go back and check and see if you can figure out if there was a, just a minor mistake you kind of carried through the whole problem. So those are just some tips when approaching these problems. Another thing to be able to do is to calculate a density. Density is one of those derived units. It's mass per unit volume. And with all of these formulas that you're going to see, you need to be able to rearrange them to solve for any of the values that are shown. So for example, given a density and a mass, solving for a volume, or given a volume and a density, solving for mass, or solving for density. So any of those combinations could be asked for, and you could use this formula to do those and to come up with a value. You want to make sure always when you're doing these calculations that your units are compatible and the same. So for example, in density measurements, you'll notice that the units here are grams per cubic centimeter. Those are the units that were given for mass and volume. You just want to make sure that all of those match up. So if you're given a mass in grams and a volume in, say, milliliters, then obviously your units for density are grams per milliliters instead. So it's always a good idea to make sure that all of those units match up as they should. This is, I said, a different way to calculate a volume using the density equation. Again, just rearrange and solve for volume here. You always want to make sure that the units do cancel to give you the units that you're looking for. Cubic centimeters, we know, are a unit of volume, so that makes sense in terms of the units that were given. If you do that and check that the units make sense to the measurement that or the calculation you're making, that's another good way to make sure that you're solving the formula or the problem correctly. Significant figures we've talked about, so here's an example giving you some practice with how many significant figures you have. I know we've spent a good deal of time on this, so I'll skip through this, but there are extra problems here, so if you are still having difficulty with these, I would suggest you work these problems or, again, any of the problems in your text as well. We talked about this as well, calculation using significant figures, so figuring out how many significant figures to report your answer to. In terms of the exam, the midterm and the final, you'll see typically 3 significant figures most answers. That's just because most measurements that we make typically involve 3 or 4 significant figures. So that's kind of another ballpark check on the work that you're doing. If you end up with a significant figure of 1, you probably did something incorrect. Likewise, if you end up with a significant figures of, say, 7, it's unlikely that that's correct. You'd need to, that would be a red flag to go back and just make sure that you have everything correct. Here's a unit conversion, and again, using significant figures example. You should be able to convert units. You will see that that comes up quite a bit. In fact, one of the things that you want to check for when you initially read through a problem is to see what units you're given and what units are being asked for in the answer. Oftentimes, one of the mistakes that students will make is just not doing that unit conversion, and then you don't get the correct answer just because of that. It is a detail to make sure that you pay attention to as you're solving these problems. So make sure that the units that are being asked for in the answer are the ones that you have converted correctly to. Okay, so Chapter 1. In terms of what we're going to talk about for Chapter 1, I'm not going to focus on all of the qualities and characteristics of the elements. It is interesting information, and obviously that's one of the reasons I like chemistry, but in terms of asking you to tell me about it on an exam, I'm not going to expect you to be able to do that. In terms of the names and symbols, the periodic table that you'll be given on the exam will have the names written under the symbols for the elements, so you do not need to memorize those. However, after getting used to them for a little bit, you'll probably know a few of them just by repetitive use, but I will not ask that you memorize the symbols and the names. So here is a periodic table. This one does not have the names underneath, but it does have the rest of the information that you would be given on the copy of the periodic table on the exam. So you will be given your copy will have the group names. We'll use the A and B system that you see here, so 1A, 2A, and 1B, 2B, for example. Your copy will not have the line that denotes metals and nonmetals, so you'll want to make sure that you know where that is. I will ask you examples like, tell me, is silicon a metal, semi-metal, or non-metal? And the correct answer obviously would be semi-metal. So you should know where that ladder is. It does denote the metals and nonmetals. You'll notice the semi-metals are all of those boxes, all of those elements that touch it, with the exception of aluminum, which is atomic number 13, and polonium, atomic number 84. But the rest of those are considered semi-metals. To the left of the stair, not touching it, are your metals, and to the right are your nonmetals. Hydrogen is placed in group 1, but it is a nonmetal, just to note that, even though it's found over on the left-hand side. So some common groups of elements and their properties. I'm not going to ask you individual properties for groups, but you should be aware of just this general information. So a property is something that we use to describe or identify matter. We break that up into one of two types, intensive or extensive properties. Intensive properties do not depend on the amount of the sample that you have, so temperature and melting point are good examples here. So it doesn't matter if I have a cup of water or a gallon of water. If they're both sitting on my table, their temperature would be identical because they're in the same environment. Likewise, the melting point of water does not change regardless of how much water you have. Extensive properties do depend on size, so things like length, volume, obviously mass would be examples of extensive properties. Another way that we describe matter are by physical and chemical properties. Physical properties are those that do not involve a change in the chemical makeup of the sample. So these could be things like temperature, solubility, hardness, melting point. These are not things that measure any type of chemical change. Chemical properties are characteristics that do involve a change, so they are properties describing a chemical change in a substance. So rusting, tarnishing, hardening of cement is given there as an example. So these are chemical reactions that are occurring, and so the properties describing them are considered chemical properties. Okay, a little bit about the groups here, and I'm just going to go through the I think there's just 4 here that are labeled, and you should know the names of these groups. So group 1A are known as the alkali metals. These do not include, this does not include hydrogen. That's the one at the very top. It's placed there mainly because it's atomic number 1. Sometimes you'll see it in periodic tables sort of off to the side. But it is not part of the alkali metal group, even though it is part of group 1A. You'll see why the numbers matter, so where the group 1A, how that plays into the chemistry of these different elements. Group 2A are known as the alkaline earth metals. Group 7A are the halogens. And group 8A are the noble gases. So those are the 4 groups that I'll expect you can tell the names of those groups. The rest also have names, but we'll not go into those in the context of this course. Again, I denoted where you should know where metals are. So if I gave you any atomic number, you should be able to identify if that particular element is a metal or a nonmetal or a semi-metal. And again, knowing where that line is, or just memorizing those few semi-metals will help you there. Excuse me. Okay, we talked about a little bit of this in the class discussion, but the next piece here is on conservation of mass and the law of definite proportions. Here's where we start talking a little bit about chemical reactions. So we will not get into chemical formulas in the context of this chapter. Those will come up shortly. But what you see here is representing a chemical equation. So on the left are the reactants and on the right are the products. And we'll talk more about how we make those formulas and where those numbers in front come from in a little while. But if we were to look at this and then look at an actual reaction, so if we took, this is going to describe a different reaction, but if we took some solid potassium iodide and solid mercuric nitrate and weighed and dissolved it into water, so it's being shown in the slide in the middle. So the solutions are mixed and they give a solid product of mercuric iodide. And then you can evaporate the rest and you get the other product, which is potassium nitrate. So if you took the masses of what you started with here, and that's what's given here, so you take the masses you started with and the masses that in the result, the sum total has to remain the same. And this comes from the law of conservation of mass, that mass is neither created nor destroyed in chemical reactions. Obviously, this does not apply to nuclear reactions, so if you're thinking about those, we're specifically talking here about chemical reactions, and the law does apply to chemical reactions. So we can take the total amount of reactants that we started with, 6.57 grams, and again, assuming ideal conditions, meaning that all of the reactants react to form all of the products that you see here, the total of the mass of the products would also be the same. In reality, most reactions don't go to completion, so you're left with one or more of the products. We'll talk later about that in terms of percent yield and how you would apply that to these types of problems. And just in general, if you were doing this reaction in the laboratory, you would most likely have one of those two products left. It's also common to see some byproducts in some reactions. We'll not talk about that in this course, but if you take future courses, you may come across that. Law of definite proportions tells us that we can take pure chemical compounds and that different samples of them always contain the same proportion of elements by mass. So if we take water, doesn't matter where we take that water from or how many different samples we take, its elemental composition is still the same. It's 2 hydrogen atoms and 1 oxygen atom combined together to make that water. So they combine in specific proportions. It's not at random. The law of multiple proportions tells us that elements can combine in different ways to form different chemical compounds. So this just tells us that, say, hydrogen and oxygen can combine together to form water. And so in that case, there's 2 hydrogen atoms and 1 oxygen atom in every molecule of water that we have. Or we could take, say, hydrogen peroxide. And if we analyze that, we'd see that there were 2 hydrogen atoms for every 2 oxygen atoms in that molecule. So that's what the law of multiple proportions tells us, that while we can have, we always know water has 2 hydrogen atoms and 1 oxygen atom, we can also combine hydrogen and oxygen together differently, form a different compound, as in the example of hydrogen peroxide. Also, this connects to masses, so the mass of water and the mass of hydrogen peroxide in those 2 examples I just gave would be different. Likewise, in the example you see here, if we take nitric oxide and nitrous oxide, so those are different numbers of atoms combined together, they're different masses. So here, nitric oxide would be 1 nitrogen atom and 1 oxygen atom combined together. And I'm sort of getting ahead here, but we'll talk in a bit about how you know the masses of these. So that 7 grams of nitrogen means it's 1 nitrogen atom. 8 grams of oxygen is 1 oxygen atom. So if you look at nitrous oxide, it's 7 grams of nitrogen per 16 grams of oxygen. So you can probably figure out that's 1 nitrogen for every 2 oxygen atoms that combine together to form nitrous oxide. So again, two different compounds, but they themselves have a specific arrangement of the atoms and a specific mass as well. Here's just a picture of showing that, how they combine together. Somebody asked me the difference between the law of definite proportions and the law of multiple proportions. The law of definite proportion tells us how individual molecules form. So the first one, there's one nitrogen atom and one oxygen atom. So nitric oxide always combines in that way. Nitrous oxide always combines with one nitrogen atom and two oxygen atoms. That's the law of definite proportions. Law of multiple proportions tells us that we can take nitrogen and oxygen and combine them in different ways. And when we do that, we form different compounds. So they're related but not the same. This is an example that uses the law of multiple proportions. We didn't go through this in class, so I will talk through this a little bit. So here's an example where you're given methane and propane. You're given that a sample of methane contains 5.7 grams of carbon atoms and 1.9 grams of hydrogen atoms that are combined in a certain way. And a sample of propane contains 4.47 grams of carbon and 0.993 grams of hydrogens combined in a different way. And it says, show that the two compounds obey the law of proportion. So what you're looking for here is to find a whole number ratio between carbon and hydrogen. If you remember from, let's see, I don't know if this was 5th grade math or something like that, where you're finding, the number, trying to find whole numbers that that correspond to the ratio between two non-whole numbers. That's essentially what you're doing here. So what you're given is, in the first one, methane 5.7 grams and hydrogen is 1.9 grams. If you divide the larger by the smaller, you'll see you get 3, as an example there. And in propane, the carbon-hydrogen mass ratio, again doing the same thing, divide the smaller by the larger, you end up with 4.5. And then if you take those two and divide them, you see that the ratio is 2 to 3. So we get a whole number ratio. So that represents the fact that these compounds obey the law of multiple proportions. We'll talk a little bit further on later how we can also use this to do calculations and figure out what the actual formulas of compounds are. That will come later. So here are just some of the main components of Dalton's atomic theory. Elements are made up of tiny particles called atoms. We know each element has a particular mass of its atoms, that atoms of that element always have the same mass, but atoms of different elements have different masses, and that we can combine elements together to make different compounds. When we do that, they combine together, the atoms combine together in small whole number ratios. Chemical reactions only rearrange how the atoms are combined, so the atoms themselves don't change. Nuclear reactions obviously represent ones where the atoms themselves can change. Some of the ways that we discovered the types of particles of atoms, so these are just going to show you some of the very critical reactions, experiments that showed us this. So J.J. Thomson used cathode ray tubes, and you can pass an electron beam through these tubes. You can see that there's an anode, a positive end, and an anode, a positive end, and a cathode, the negative end. And you can pass those electrons through. You can actually see them as that sort of white-looking beam going through. And what he found is that if you apply a magnetic field, in this case just holding the magnet up to that tube, that the beam is deflected. So this said sort of first that there are some particles that are there that are passing through, and that if he applies that magnetic field, he can see that that ray gets bent, and because of the direction of the bending of the ray, could discover that they were negatively charged because they were attracted to the positive end of the positive pole of the magnet. Another key experiment was Millikan's oil drop experiment. This is one where he discovered what both the charge and the mass of these oil droplets were. So I'm not going to go through this experiment at length, but anyway, that's how we got this sort of charge to mass ratio that we now know about electrons. And then Rutherford used what's known as the gold foil experiment, and directed a beam of alpha particles, which I'll talk about sort of at the end here, in terms of the nuclear chemistry. And he found that most of them passed through, but a very small number did not. They were deflected. And so he explained that there must be something in that gold, so obviously these are atoms of gold, that's made up of empty space, and that there's some other part of it that's a concentrated mass that has a central core, and he named that the nucleus, so he's known for discovering the atomic nucleus. And here's just a sort of picture of that experiment that he conducted. Okay, we looked at this table again in terms of the discussion. You should know the three main particles, subatomic particles of the atom: electron, proton, and neutron. That the proton and neutron are the same mass and also make up the majority of the mass of an atom. They're found in the nucleus. And that the charges, so an electron is negatively charged, the proton is positively charged, and they're exactly the same quantity of charge but opposite in sign to each other. And obviously, the neutron has no charge. So now we start getting into some of the characteristics of different elements. Atomic number, this is the number of protons in an atom's nucleus. It's also the identification number that we see on the periodic table, so it identifies a particular element. If that atoms of those atoms are not charged, meaning they're not ions, then it's also the number that's equivalent to the number of electrons that surround an atom's nucleus of that element. Mass number, this is equal to the sum of protons and neutrons. We'll take a look at a few of these. And isotopes, these are atoms that have the same atomic number, but different mass numbers. So they're atoms of the same element, but have different masses. We'll take a look at a few of these. So this is two different isotopes of nitrogen, nitrogen-14 and nitrogen-15. What you see there, with the chemical symbol and the numbers, that's representing that isotope. So I think one of the problems in the homework asks to write an isotope symbol. It's always written in this way with the numbers on the left. The number on the top left is the mass number, and the bottom left is the atomic number. Note that the atomic number here is 7. It identifies nitrogen. If it were 8, that would not be nitrogen. So the atomic number both identifies the element and tells you the number of protons. It's also equivalent to the number of electrons if the element's not charged. The name nitrogen-14, when you're given that name, the 14 tells you the mass number for that isotope. So you'll see there nitrogen-14 written with its mass number. Nitrogen-15 obviously has a mass number of 15. The mass number being the sum of protons and neutrons. So from anytime you're given a mass number and an atomic number, you can easily figure out the number of protons, neutrons, and electrons for that element. So if you take nitrogen-14, for example, atomic number is 7. That means it has 7 protons. There's no charge, so it means it has 7 electrons. Mass number is 14, so take away 7 from that, and you get the 7 neutrons. And again, nitrogen-15, the only difference is that extra neutron, so it has 8. Here we start talking about masses and atomic weights. Now, we did a little bit of this in the discussion. So we have defined the masses of all the elements. You'll see those written as atomic weights on the periodic table. They're usually underneath the chemical symbol, as you see here. That number, that atomic weight, is actually a weighted average of the masses of that element's naturally occurring isotopes. And I'll show you in a little bit of calculation involving that. When we use these to calculate formula weights, which you also will have to do, say, calculate the formula weight for methane, which is CH4, you round that number. So the weight of carbon you would use for that formula weight would be 12. So this is just a common practice that we do. Hydrogen is 1. So the formula weight for methane, CH4, would be 12 plus 4 times 1, or 16. So when you're calculating formula weights, you don't carry through all those numbers, all the digits you see there, round to the nearest number and use that for calculating your formula weights. I don't think I said that in the discussion. I wanted to make sure that I said that here. Okay, so here's how that calculation is done. I know we did discuss this already. So the two naturally occurring isotopes of carbon are carbon-12 and 13. Typically there's 2 or 3 isotopes for every different element. Sometimes there's only one. So carbon-12 obviously has 6 protons, 6 neutrons, and 6 electrons. Carbon-13 would have 6 protons, 6 electrons, and 7 neutrons. And so that you can see the difference in the masses. The 12 versus the 13.0034 comes from that additional neutron. And then you're given percent abundance, so what we naturally find them as. You can use that percent and their individual masses to calculate the average atomic weight, and that's what you can see at the bottom. You should know how to calculate these, and I know there's 1 or 2 examples that are given in your text. So essentially you are converting the percent to a decimal, and then calculating an average, so multiplying the percent by its weight, and adding that to the next 1% and its weight, and then summing them together. This will give you the average. We talked a bit about Avogadro's number. Again, this is a number a specific number, so it tells us that a mole of any element contains 6.022141 times 10 to the 23rd atoms. You can use just the 6.022. Sometimes you'll see it reported as 6.023. Either one will work for calculations that we do, so you don't need that extra 141 in your computations that you're doing. So it is just a number. It's a number that describes a mole and the equivalent number of particles of that mole. So we talked about a mole of donuts. So if you had a mole of donuts, somebody said we'd have diabetes, and that's most definitely for sure, if we ate all those donuts. So a mole of donuts would be 6.022 times 10 to the 23rd donuts. A mole of bricks would be 6.022 times 10 to the 23rd bricks. I find that helps students kind of conceptualize this idea of a mole and Avogadro's number. And then obviously applying it to chemistry, we're talking about atoms and molecules. We didn't do one of these in the discussion, but be thinking about how that applies. So if we have a mole of hydrogen atoms, we have 6.022 times 10 to the 23rd hydrogen atoms. If we have a mole of water molecules, and I asked you how many water molecules we had, you would say 6.022 times 10 to the 23rd molecules. So it can apply to molecules as well. We can do different types of, I don't know if tricks is the right word, but different types of descriptions here. So I could ask you a problem like this. If you have a mole of water molecules, how many hydrogen atoms do you have? So water is H2O. That means that there's 2 hydrogen atoms in every water molecule. So if I have a mole of water molecules, I have 2 times Avogadro's number of hydrogen atoms. So those types of calculations you need to be able to do also. So be thinking in terms of, again, what the problem gave you and what they're asking for in an answer, and making sure you're thinking through that. And obviously writing things down as you go as well. Molar mass, mass in grams of 1 mole of any element. This is equivalent to its atomic weight. We talked a bit about calculating formula weights for compounds and how to go about doing that. So if we take the example here of silver, a mole of silver is its atomic weight. So a mole of silver is 107.868 grams. If I have a mole of silver atoms, so they're given a couple of examples here. So that gives you how many silver atoms I have. This is just showing a picture of a mole of different things, and I honestly don't remember what's in each of the categories, but it's just showing you that a mole is a quantity, so the masses of those things will differ. So a mole of hydrogen atoms has a different mass than a mole of oxygen atoms. A mole of oxygen atoms has a different mass than a mole of carbon atoms. Okay, but the number of atoms you have is the same. That's because each of those atoms has a different mass. An atom of oxygen, it has a higher mass than an atom of hydrogen. This is just a general conversion, so I'm going to skip over this. This is just using atomic size, but it's essentially just a unit conversion. This is a type that we talked about. I think we actually did this one or talked through it. So again, given two isotopes of chlorine as an example here, and their respective percent abundances, calculating their overall formula mass. One note here, you'll notice that they use the unit AMU, the 35.45 AMU. That stands for atomic mass units. You can use that unit, AMU, or grams per mole. Either of those is the same, represents the same unit. So you could say that the atomic mass is 35.45 AMUs or 35.45 grams per mole. You'll see that most of the time when we're doing these calculations, we'll use grams per mole. But just to note, AMU is an identical unit. We talked a bit about how we do these conversions now that we have these basically two conversion factors, right? We know that a mole of anything has Avogadro's number of that thing. So a mole of donuts has 6.02 times 10 to the 23rd donuts. We also know now that a mole of any particular element has the mass that's listed on the periodic table. So here's an example. How many moles and how many atoms of silicon are in a sample weighing 10.53 grams? And they're giving you the atomic mass of silicon, and you could have looked this up on the table as well. So get used to not having that second piece and just looking that up. So we know that it's 28.0855 grams per mole. Again, if you think in those units, it makes it more helpful, I think, to do these types of calculations. So that tells us that a mole of silicon has a mass of 28.0855 grams. They give us 10.53 grams. So we set up our conversion factor. We have grams on the top in the 10.53 grams of silicon. So we need grams on the bottom in our conversion factor. So 28.08855 grams of silicon goes on the bottom, and 1 mole of silicon goes on the top. We are able to cancel the grams on the top and the grams on the bottom, leaving us with moles. That's what the question asked us for. So by using the units, we know that we've set it up properly. Then it's a matter of just doing entering the numbers correctly into your calculator. So it's the 10.53 divided by 28.0855 to get that number of 0.3749. You should go through these in practicing with your calculator to make sure that you are up to speed on that, especially when we start getting into log functions and scientific notation. I would definitely practice those as you're going along. The second thing asked us how many atoms we had. So we know we have 0.3749 moles. And we know a conversion factor that if we had 1 mole of silicon atoms, we'd have 6.022 times 10 to the 23rd atoms of it. So we use that to calculate our answer. Again, moles on the top is what we're given, so we want moles on the bottom in our conversion factor, so the atoms go on top. Atoms are what we're asked for in the answer, so that makes sense. And then again, we're just multiplying 0.3749 by 6.022 times 10 to the 23rd to get the answer that you see there. Again, when you start working with these exponents, I would practice these in your calculator so that isn't giving you any issues in terms of solving these problems. Okay, so those types of conversions, again, you should practice being able to go moles to atoms, grams to moles, atoms to grams, I suppose. And what you want to do here is to be thinking about what's the information that I'm given, what are they asking for, and what are the conversion factors that I know. That's kind of the approach to take when you're doing these problems. Always setting up your unit conversions, always including the units, making sure that your units cancel and leave you with the units that you want. If you always set it up that way, you will get these problems correct. If you try to rely on some type of, there are several types of memorization type things about what to do if you're trying to go from grams to moles or vice versa. Those will work most of the time, but if you get more complicated problems, they might not. So again, I recommend that you use the unit conversion method that we're doing here, canceling your units out, and so that you get the units you want. And this method always works. Okay, this last bit we did not get a chance to talk about in the discussion, but just to talk a little bit about nuclear chemistry. Again, in the context of sort of atoms, this fits in. What we're going to talk about here are 4 types of nuclear reactions, and I'm going to ask that you're able to produce the types of reactions that you see, for example, on the bottom of this screen, and we'll talk about each of those examples, and being able to identify what type of reaction it is based on the reaction formula. So nuclear chemistry obviously involves looking at the nucleus, properties and charges of atomic nuclei. So you'll notice here there's no electrons. We're talking specifically about protons and neutrons because it's nuclear chemistry. It's only involving the nucleus of the atom. And a nuclear reaction is one that changes an atomic nucleus. That makes sense. And here what you see is a nucleus of uranium. So this would be an isotope of uranium. It would be called uranium-238. You'll notice that the isotope symbols that are written are exactly like you saw before. So the mass number is on the top left, the atomic number is on the bottom left, and what you're looking at here are some changes in those numbers. So you'll see that what happens here in this case is that uranium-238 loses excuse me, loses 2 protons and 2 neutrons. So its mass number goes down by 4, and you end up with that, I think it's thorium, 234 product. And then you'll see that helium that is released. We'll talk a bit more about what that helium actually is in the context of a nuclear reaction. So in all these types that you're going to look at, you're going to see isotopes. You need to be able to see what changes are occurring in both the atomic number and the mass number, and use your knowledge of what those mean to identify what's going on. So again, just to review, the atomic number on the bottom left tells you the number of protons. So, and the mass number on the top left tells you the sum of protons and neutrons. So, for example, that uranium-238, I know it has 92 protons from its atomic number, so it must have 146 neutrons in order to sum to 238. So that's how you calculate those. These are writing symbols. You could practice these. So how do these differ from chemical reactions? I've mentioned this already, so we're looking specifically at an atom's nucleus. A chemical reaction involves how the atoms are combined, and we're looking specifically at isotopes and how they are losing those particles from their nucleus or changing in some way. Also know that the energy change that accompanies a nuclear reaction is usually far greater than that accompanying a chemical reaction. Some other terms here. So radioactivity refers to that spontaneous decay and emission of radiation from an unstable nucleus. A radioisotope is a radioactive isotope, so one that can undergo this nuclear change. Okay, so the first type of change here, or type of reaction, involves alpha radiation. Radiation in this sense here, if you think about it as being emitted or given off, that will help you in terms of these looking at these reactions. So this is the same example that I showed you at the beginning. So this is an example of a nuclear reaction involving alpha radiation. An alpha particle is the same thing as that helium-4 nucleus. So we actually know and denote that an alpha particle is a helium-4 nucleus. They are one and the same thing. So what you're seeing here is that uranium-238 emits or radiates an alpha particle, and then you can see what's left is that thorium-234. So the nuclear reaction that's shown here is similar to what you've seen in a chemical reaction, in that on the left of the arrow is what we're starting with. So on the left here is the uranium-238, so that's what we're starting with. And then the nuclear reaction is what's referenced by the arrow, in this case. And on the right are the 2 nuclear products, in this case an alpha particle and then the thorium-234. And for any of these, you should be able to calculate, as you see there, the number of protons and neutrons, talk about how many protons and neutrons are lost, for example. And it is always the case that because when you emit an alpha particle, that alpha particle has 2 protons and 2 neutrons. you will always see that what you started with, so the mass number here of 238, what you started with will lose 4 from its mass number. Those 4 being 2 protons and 2 neutrons. So the math here makes sense if you can think about it in those terms. If you look just at the blue numbers, the mass numbers, you see we started with 238 on the left. And if we sum the products on the right, we still have 238. This is really important. This should always be the case when you have nuclear reactions. So when you are writing these reactions, you should always go back and check and make sure that your numbers all add up to the same. You can also see there that the atomic numbers, the total sum is the same on the left and the right. Again, that should always be the case. So it's a good way to double check that you've written those nuclear reactions correctly, is to sum the numbers on the left and the ones on the right and make sure that the total is the same on the left and the right of the arrow. So alpha radiation emits an alpha particle. That's a helium-4 nucleus. That means that your initial isotope that you started with is going to lose 4 from its mass number. It also means it's going to lose 2 from its atomic number, right? Because that's the 2 protons that it lost as well. So it will always happen in that fashion. So the type of question to be able to answer here is to start with an isotope that you're given. You could be given an example and say this undergoes alpha radiation, write the nuclear reaction. So in this example, I would say you're starting with an isotope of uranium-238, and it is undergoing an alpha radiation event. Write the nuclear reaction, and you would write what you see at the bottom here. A second type of nuclear reaction is beta radiation. This one should look a bit different to you. Notice that the way the reaction is written is the same. So on the left, we're starting with an isotope of iodine-131. That isotope of iodine-131 has 53 protons. We know that from its atomic number. And 78 neutrons. We know that from the fact that its mass number is 131. And a beta particle, notice the beta particle is an electron. So it has no mass number. So you see there's a 0 there. And a -1 charge. Again, if you think in terms of balancing numbers here when you're writing these reactions, that will help you. As you know, conceptually, this is a bit different. So what you'll notice here then is if that beta radiation occurs and that beta particle is on the right, that means that my mass number is going to stay the same because there's 0 there for the mass number on a beta particle. So it stays as 131 on xenon. However, because it has a -1 charge, you see on the bottom left, that means that my atomic number changes from that 53 on the iodine to 54. Why? Because I need to sum to the same number on the left and the right. Notice that I have 53 on the left, so I need to have 53 on the right. If I have -1, that other number must be 54 to give me the total of 53. You cannot have charges, so the number has to be the same on both the left and right, no charges. And again, there's 131 on the left. The beta particle has no mass number, so it remains 131. But we've changed the identity of the element because we've changed the atomic number. Remember that the atomic number identifies the element. So 53 means iodine in all cases. 54 means xenon in all cases. So we have changed from an isotope of I-131 to xenon-131. And that xenon-131 has 54 protons from its atomic number and 77 neutrons because we subtract that from the 131. Gamma radiation is just a radiation of energy. We don't write nuclear reactions for these. So you would not be asked to write a reaction for these because there really isn't one. It's just, it shows the isotope at the beginning, the same isotope to the right of the arrow with an emission of energy. So you won't be asked to write reactions for those. The last two here, types of reactions. So this one is known as a positron emission. Emission meaning it's being given off. And let me move this so you can see that. So a positron here, note what that is. So a positron is something that has a 0 mass number but a +1 charge. So notice that the 1 there in the atomic number position. That means that, so if we look over on the left, we start with potassium 40. Potassium 40 undergoes positron emission. That means that the product that's left has to have an atomic number 1 less than it started. So that's where the 18 comes from. And because there's no mass to that positron, the mass number stays the same. So we're left with the 40. Again, you're looking to balance the numbers in the left and the right. And for all of these, you will need to be able to memorize that positron emission and what a positron looks like, what exactly it is. If you don't know that, you won't be able to write these reactions. So know what an alpha particle is, know what a beta particle is, know what a positron is, and then I'll show you the last one as well. And then use those numbers and use that to balance off the rest. How do we know it's argon on the right? Well, we know that the atomic number is 18 to make 18 plus 1 equal 19. And so we look on the periodic table and we'll see that atomic number 18 is argon. So that's how you identify the isotope, what type of element you have from that. And the mass number stays the same. And again, you see the calculations there for protons and neutrons. You should be able to do that for any of these isotopes that you're given. The last one here is called an electron capture. Notice the name is different, capture. And if you look at that reaction, you'll notice that the electron is on the left-hand side of the arrow. This is the only example of a nuclear reaction where we see something on the left-hand side of the arrow, besides the beginning isotope. Okay, so it is unusual in that. And the capture explains how that's going on. So an isotope of mercury-197 undergoes electron capture. Okay, means it's gaining this electron, and then you see the product gold-197. The electron there, no mass to it, so the mass number 0 has a -1 charge to it. You need to make sure that the numbers balance on the left and the right. So the mass number is 197 on the left, so that you have to have 197 on the right. You'll notice that the atomic number on the left is 80 minus 1, or 79. So that's where we get the 79 on the right. And then we look up atomic number 79, and we see that that's gold. So that's how we identify what we have. And then the mass number 197. So these are the different types of nuclear reactions that you need to be able to write. You'll either be given, you could be given, say, just the left-hand side of this reaction and asked to predict the products, or product in this case. You could be given information about that it is an electron capture and be asked to write the equation that way. So get used to both. I know that both types are given in your text. Here's some examples. So balancing nuclear equations. So A, B, and C give you the type of reaction, so alpha emission, beta emission, or positron emission, and they tell you what you're starting with. So curium-242, magnesium-28, xenon-118. And then you're asked to come up with the answers there. Looks like there's, I'm not sure where these CMs, it looks like the slide pulled through differently. So I'm going to ask that you look at the worked example in your text and not this one. There seems to be some errors here. Okay, nuclear change and radioactivity in terms of, this just gives you a summary of what we just looked at. I don't know that this is helpful. I'd rather you look at the individual reactions and be able to write them out that way. But what is helpful, I think, is the symbol part and the connection to the process. So again, alpha emission is emission of an alpha particle or that helium-4 nucleus. Beta emission is emission of that electron. And gamma emission is just energy. Positron emission is the positively charged, that +1, essentially, it forms the positron. Electron capture, I don't know why it says EC there, but electron capture is, again, the electron, but it's on the left-hand side of the reaction.